I'm so glad you found your way here. You're breathing the same air dinosaurs once breathed, recycled through forests for millions of years. Tonight, you'll discover why Earth tilts through space like a spinning top, and understand why every summer sunrise was written billions of years ago. Welcome to Get Sleepy Science. Even now, you're resting on a living planet, forests breathing oxygen, oceans cycling moisture, mountains growing inch by inch beneath your feet. Connect with this world supporting you. We'll discover 100 nature facts about Earth's seasonal rhythm, from the ancient collision that tilted our world sideways, to trees measuring daylight with molecular clocks, to the dance between darkness and light that governs all life. These calm explorations of Earth's wisdom plant seeds of tranquility in restless hearts. Sharing this gentle science creates a pathway for more nature lovers to discover this healing ground, one sleepy soul at a time. Your presence here nurtures our growing forest of peace. Sink into your favorite resting spot. Allow your muscles to release, each breath growing softer. There's no need to remember these geological facts. Just notice that warm, drowsy calm washing over you, like gentle ocean waves pulling back from shore, each one drawing you deeper into restful, effortless sleep. Close your eyes and breathe deeply. You're resting where ancient trees whisper secrets of eternal wisdom. Let your mind sync with nature's calm. And now we begin. Earth doesn't stand up straight. As it travels around the Sunday, our planet tilts at an angle of 23.4 degrees, leaning like a spinning top that never quite rights itself. This inclination happened about 4.5 billion years ago, when something enormous, perhaps a Mars-sized planet, crashed into the young Earth during the solar system's chaotic formation. That ancient collision gently nudged our world sideways, and it's remained tilted ever since, creating the eternal dance of seasons we experience today. Without that angle, Earth would have no seasons at all, just endless sameness, with each day identical to the last, no matter where you lived on the planet. Here's something remarkable about Earth's axial orientation. As our planet orbits the Sun throughout the year, the direction of that angle always points toward the same spot in space. Imagine Earth as a spinning top traveling around a table. The top's axis always points in the same direction, even as it circles. Currently, Earth's North Pole points toward Polaris, the North Star. This constant direction means that during half of Earth's orbit, the northern hemisphere leans toward the Sun, receiving more direct sunlight. 6 months later, on the opposite side of the orbit, the southern hemisphere leans toward the Sun instead. This unchanging inclination, combined with Earth's yearly journey around the Sun, creates the predictable cycle of seasons. Many people believe Earth is closer to the Sun during summer, making it warmer, and farther away during winter, making it colder. This seems logical, but it's actually backward. Earth reaches its closest point to the Sun, called perihelion, in early January, when it's winter in the northern hemisphere. Earth's farthest point, aphelion, happens in early July, during northern hemisphere summer. The distance varies by about 3 million miles, from 91.4 million miles to 94.5 million miles. While that sounds enormous, it's only a 3% difference in a 93 million mile journey, far too small to explain the dramatic temperature changes we experience between seasons. The real cause is something entirely different. The secret to seasons lies not in distance, but in angles. Specifically, the angle at which sunlight strikes Earth's surface. When the northern hemisphere leans toward the Sun during summer, sunlight arrives almost straight down, hitting the ground at a steep angle. This concentrated sunlight delivers more energy to each square foot of surface. During winter, that same hemisphere tilts away, causing sunlight to arrive at a shallow angle, spreading the same amount of energy across a much larger area. Think of a flashlight shining straight down versus at a slant. The slanted beam creates a wider, dimmer circle of light. That's why summer feels warm and winter feels cold. The axial orientation also determines how many hours of daylight each part of Earth receives throughout the year. During summer in the northern hemisphere, the North Pole tilts toward the sun, keeping northern latitudes in sunlight for more hours each day. The days grow longer, giving the sun more time to warm the land and air. During winter, the opposite happens. The North Pole leans away, shortening the days and lengthening the nights. Less daylight means less time for the sun to heat Earth's surface, and more time for that warmth to radiate back into space during the long, dark nights. This combination of angle and duration creates the seasonal temperature swings we know so well. Twice each year, Earth reaches a point in its orbit where neither hemisphere leans toward or away from the Sunday. These moments are called equinoxes, from Latin words meaning equal night. During an equinox, day and night are nearly the same length everywhere on Earth, about 12 hours each. The spring equinox happens around March 20th, marking the beginning of spring in the northern hemisphere and fall in the southern hemisphere. The autumn equinox occurs around September 22nd, reversing the seasons. At the equator, the sun appears directly overhead at noon during both equinoxes. These transition points mark the moments when Earth's orientation shifts from favoring one hemisphere to favoring the other. The solstices represent the most pronounced points of Earth's seasonal journey. During the summer solstice around June 21st, the northern hemisphere reaches its maximum lean toward the sun, creating the longest day and shortest night of the year for northern latitudes. 6 months later, around December 21st, the winter solstice brings the opposite, the shortest day and longest night as the northern hemisphere tilts to its maximum angle away from the Sunday. At the moment of the summer solstice, the sun appears directly overhead at the Tropic of Cancer, an imaginary line 23.4 degrees north of the equator. During the winter solstice, it shines straight down on the Tropic of Capricorn, 23.4 degrees south. Something extraordinary happens near Earth's poles during summer solstice. Above the Arctic Circle, at 66.5 degrees north latitude, the sun doesn't set at all for at least 24 hours. This phenomenon, called the midnight sun, occurs because the Earth's orientation is so pronounced that the entire Arctic region remains in sunlight as the planet rotates. The closer you get to the North Pole, the longer this lasts. At the pole itself, the sun stays above the horizon for 6 full months, from the spring equinox until the autumn equinox. It's an endless day, with the sun circling horizontally around the sky, never rising high overhead but never dipping below the horizon either. The opposite of the midnight sun is equally striking. During winter, regions above the Arctic Circle experience polar night, a period when the sun never rises above the horizon. The angle that brings summer's endless daylight now keeps the Arctic in shadow. At the North Pole, this darkness lasts for 6 months, from the autumn equinox to the spring equinox. It's not complete blackness though. During most of polar night, there's twilight for several hours each day as the sun hovers just below the horizon. Only during the deepest part of winter, for about 2 months at the pole, does true darkness reign, with no hint of sunlight whatsoever. Earth doesn't travel in a perfect circle around the sun. Its orbit is slightly elliptical, shaped like a stretched circle or oval. This means Earth's distance from the sun changes throughout the year. As of December 2025, precise measurements show that at perihelion in early January, Earth comes within 91,405,993 miles of the Sunday. At aphelion in early July, that distance stretches to 94,502,939 miles. This 3.1 million mile difference might sound huge, but compared to the average distance of about 93 million miles, It represents only a 3.3% variation. This small change affects the total amount of sunlight Earth receives, but the effect is overwhelmed by the much more powerful influence of our planet's axial orientation. When it's summer in North America, Europe, and Asia, it's winter in Australia, South Africa, and South America. This isn't because the southern hemisphere is somehow farther from the sun. Remember, distance doesn't determine seasons. Instead, when the northern hemisphere leans toward the sun, the southern hemisphere automatically tilts away by the same angle. 6 months later, the situation reverses. This means Christmas in Australia happens during summer, with beach weather and warm temperatures, while July brings winter chill. The timing of seasons is entirely dependent on which hemisphere you're standing in, creating a planet where summer and winter always exist simultaneously, just in different locations. Near the equator, between the tropics of Cancer and Capricorn, seasons work differently. These tropical regions never lean far from the sun's direct rays, so temperatures remain fairly constant year-round. Instead of winter and summer, many tropical areas experience wet and dry seasons, driven more by shifting wind patterns and rainfall than by temperature changes. The sun always rises high in the sky here, delivering strong, direct sunlight regardless of the time of year. This is why tropical rainforests can thrive with their incredible biodiversity. The consistent warmth and predictable light create stable conditions that allow life to flourish in its most varied and colorful forms. Earth's 23.4-degree orientation isn't permanent. It actually changes over incredibly long time periods. According to current measurements from December 2025, Earth's axial angle is 23.43591 degrees, and it's decreasing very slowly at a rate of about 0.00001 degrees per month. Over a cycle lasting approximately 41,000 years, this angle oscillates between 22.1 and 24.5 degrees. Right now, we're roughly halfway through this cycle. Earth last reached its maximum inclination of 24.5 degrees about 10,000 years ago, and will reach its minimum of 22.1 degrees about 10,000 years from now. These changes significantly affect long-term climate patterns and ice age cycles. The slow changes in Earth's axial angle play a crucial role in triggering ice ages. When the orientation is at its maximum, 24.5 degrees, seasons become more pronounced. Summers get hotter and winters get colder. When the angle decreases toward its minimum, 22.1 degrees, seasons become milder, with cooler summers and warmer winters. Scientists have discovered that cooler summers are actually more important for ice age formation than colder winters. During mild summers, snow and ice that accumulated during winter doesn't completely melt. Year after year, this leftover ice builds up, eventually forming massive ice sheets that can cover entire continents. These glacial cycles, driven partly by angular variations, profoundly shape Earth's climate history. The collision that created Earth's orientation happened during what scientists call the Late Heavy Bombardment period, about 4.5 billion years ago. The impacting object, sometimes called Theia, was probably the size of Mars, about half of Earth's diameter. When it struck, the impact was so powerful that it vaporized both Theia and part of Earth's surface, creating a cloud of debris that orbited our planet. That debris eventually coalesced to form the Moon. This means the same cosmic accident that gave Earth its seasons also gave us our Moon. Without that ancient collision, our planet would stand upright. Our days and nights would always be equal, and life as we know it, shaped by seasons, might never have evolved. Earth's rotation axis doesn't just lean, it also wobbles slowly, like a spinning top that's winding down. This wobble, called precession, takes about 26,000 years to complete one full cycle. Currently, Earth's North Pole points toward Polaris, our North Star. But 5,000 years ago, during the time of ancient Egypt, the North Pole pointed toward a different star called Thuban in the constellation Draco. In another 12,000 years, the North Pole will point toward the bright star Vega instead. This wobble changes when perihelion and aphelion occur relative to the seasons. Today, Earth is closest to the Sun during Northern Hemisphere winter, but in 13,000 years, it will be closest during Northern Hemisphere summer. Scientists track Earth's position using incredibly precise measurements from satellites and ground-based telescopes. They can determine Earth's distance from the Sun to within a few kilometers, and they know the exact moment of each equinox and solstice to within seconds. These measurements have revealed that Earth's orbit, inclination, and wobble all follow predictable mathematical patterns. By understanding these patterns, astronomers can calculate exactly when solstices and equinoxes occurred in the past or will occur in the future, going back or forward thousands of years. This precision has helped us understand ancient calendars, predict long-term climate changes, and even plan space missions to other planets. Earth takes 365.2422 days to complete one orbit around the Sun, not exactly 365 days. That extra quarter day creates a problem for calendars. If we used only 365 days per year, the seasons would slowly drift, with summer eventually arriving in December after enough centuries passed. To fix this, we add an extra day every 4 years, February 29th during leap years. This keeps our calendar aligned with Earth's actual orbit. But even this isn't perfect. The orbital year is slightly less than 365.25 days, so we skip some leap years. Century years, like 1900, don't get a leap day unless they're divisible by 400, like 2000. This complex system keeps seasons arriving on schedule. Earth's orbit around the Sun defines an imaginary flat surface called the ecliptic plane. If you could see this plane from space, it would look like an enormous disk with the Sun at the center and Earth traveling along its edge. Most other planets in our solar system orbit close to this same plane, which is why all the planets appear to move along a similar path across our sky. Earth's orientation means our axis isn't perpendicular to this plane. It's angled 23.4 degrees away from vertical. This relationship between Earth's tilted axis and the ecliptic plane creates the apparent path the Sun takes across the sky throughout the year, rising and setting at different points. Imagine extending Earth's equator outward into space. That creates the celestial equator, an imaginary line circling the sky. Because Earth is angled, the Sun doesn't follow the celestial equator. Instead, the Sun moves above it for half the year, spring and summer in the northern hemisphere, and below it for the other half, fall and winter. The Sun crosses the celestial equator exactly twice each year, at the spring and autumn equinoxes. These crossing points are directly east on the horizon at sunrise and directly west at sunset, which is why ancient cultures often built monuments aligned to these directions. The solstices occur when the Sun reaches its maximum distance above or below the celestial equator. If you photographed the Sun from the same spot at exactly the same time every day for a year, the images would form a figure-8 pattern in the sky, called an analemma. This shape results from the combination of Earth's tilted axis and elliptical orbit. The inclination makes the Sun appear higher in summer and lower in winter, creating the vertical component of the figure-8. The elliptical orbit causes Earth's rotation speed to vary slightly throughout the year, making the Sun appear to shift east and west, creating the horizontal component. This beautiful pattern demonstrates how Earth's two major motions, orientation and orbit, work together to create the complexity of our seasons. The transition between summer and winter doesn't happen instantly. It takes months, as Earth gradually moves from one side of its orbit to the other. This creates the intermediate seasons of spring and fall, periods when neither hemisphere is angled strongly toward or away from the Sunday. Spring represents the warming transition from winter to summer, as the inclination increases in your favor. Fall marks the cooling transition from summer to winter, as the angle moves against you. Each season lasts about 3 months, corresponding to 1/4 of Earth's yearly orbit. These transitions are gentler near the equator and more dramatic as you move toward the poles, where the change from summer to winter feels more abrupt. Earth isn't the only planet with seasons. Any planet with an axial lean experiences them. Mars tilts at 25 degrees, very similar to Earth, giving it seasons that would feel familiar, though they last twice as long because Mars takes 2 Earth years to orbit the Sunday. Uranus has the most unusual inclination in our solar system at 98 degrees. It's essentially rolling on its side as it orbits. This means Uranus's poles experience 42 years of continuous sunlight, followed by 42 years of darkness. Jupiter, with an angle of only 3 degrees, has almost no seasons at all. Understanding seasons on other worlds helps us appreciate how special Earth's 23.4-degree orientation is for creating predictable, moderate seasons. Every year, the seasons return with remarkable precision. Summer follows spring, which follows winter, which follows fall, in an endless cycle that has continued for billions of years and will continue for billions more. This predictability arises from the unwavering nature of Earth's orbit and axial angle. Barring some catastrophic collision or gravitational disturbance, nothing will change this pattern. The winter solstice will always occur around December 21st, the spring equinox around March 20th, summer solstice around June 21st, and autumn equinox around September 22nd. This reliability has allowed life to evolve intricate timing mechanisms to synchronize with seasons, and human civilizations to develop agriculture, calendars, and cultural traditions tied to the seasonal wheel. So yes, Earth's 23.4-degree inclination is changing how we understand not just seasons, but our entire planet's story. That ancient collision didn't just knock Earth sideways, it created a world where life could flourish through the rhythm of change. The angle ensures that every region, except the extreme poles, receives adequate sunlight for part of the year, preventing permanent ice caps from covering most of the planet. It drives ocean currents, wind patterns, and weather systems. It pushes life to adapt, evolve, and diversify. Without that orientation, Earth would be a fundamentally different world, perhaps one where life never became as complex or varied. The seasons are not just weather patterns, they're the heartbeat of a living planet. Let's pause here and notice your body. As you breathe out slowly, appreciate each tiny cell inside, trillions of organisms working in silence, heart beating, lungs breathing, brain thinking, all without your command. Notice the gentle sensations on your skin, in your muscles, along your spine. You are a complete ecosystem, diverse, self-balancing. Now we continue. The northern and southern hemispheres experience seasons at opposite times, but they don't experience them with equal intensity. Southern hemisphere summers are actually slightly warmer than northern hemisphere summers because Earth reaches perihelion, its closest point to the Sun, during southern hemisphere summer in January. Those extra 3 million miles of proximity increase the solar energy reaching the south by about 7%. Conversely, southern winters are slightly colder because they coincide with aphelion in July. However, this effect is moderated by the fact that the southern hemisphere contains far more ocean than the northern hemisphere, and water heats and cools more slowly than land, creating a buffering effect that smooths out temperature extremes. The warmest days of summer don't occur at the summer solstice in June, even though that's when the northern hemisphere receives the most direct sunlight. Instead, the hottest weather typically arrives in July or August. Similarly, the coldest winter days usually come in January or February, not at the winter solstice in December. This delay is called thermal lag, and it happens because land, and especially oceans, take time to heat up and cool down. Think of turning on an oven. It doesn't reach maximum temperature instantly. Earth's surface continues warming even after the solstice, because it's still absorbing more heat than it's radiating away. Only after this balance tips does cooling begin. Earth's surface is a patchwork of land and water, and these materials respond very differently to the sun's energy. Land surfaces heat up quickly during summer days and cool down quickly during winter nights. Water, with its higher heat capacity, changes temperature much more slowly. This is why coastal regions experience milder seasons than inland areas at the same latitude. The ocean stores summer heat and releases it slowly during winter, warming nearby land. In summer, the ocean remains cooler than land, providing a refreshing influence. Large inland areas far from oceans experience more pronounced seasonal temperature swings, hotter summers and colder winters, because there's no large water body nearby to moderate the changes. Your distance from the equator dramatically affects how pronounced your seasons feel. At the equator, located at 0 degrees latitude, seasons are barely noticeable. Temperatures stay warm year-round, because the sun is always high in the sky. As you move toward the poles, seasonal contrasts intensify. At mid-latitudes, between 30 and 60 degrees, you experience clear, distinct four-season patterns. Above 60 degrees north or south, seasons become dramatic, with long, dark winters and bright, nearly endless summer days. At the poles themselves, the year divides into just 2 seasons, 6 months of daylight and 6 months of darkness. The strength of seasonal change is directly proportional to your latitude. Elevation creates its own seasonal variations. As you climb in altitude, temperatures drop by about 3.5 degrees Fahrenheit for every 1,000 feet gained. This means mountaintops can experience winter conditions even during summer at lower elevations. In tropical regions near the equator, where ground-level temperatures barely change all year, climbing a high mountain takes you through multiple climate zones, from tropical forest at the base, through temperate forests, then alpine meadows, and finally to permanent snow and ice at the summit. This vertical journey compresses what would normally require traveling thousands of miles toward the poles into just a few vertical miles. Mountains create seasons by altitude. The sun's changing position in the sky throughout the year creates a simple but remarkable effect: the length of shadows. During summer in the northern hemisphere, when the sun climbs high overhead, shadows are short at midday. A 6-foot person might cast a shadow only 3 feet long. During winter, with the sun low in the sky, that same person at the same time of day might cast a shadow 15 feet long or more. Ancient civilizations used this phenomenon to track the passage of seasons. Stonehenge, the pyramids, and countless other monuments align with the sun's position at solstices and equinoxes, their shadows marking the turning points of the year with stone precision. Watch the sun throughout the year, and you'll notice its path across the sky changes dramatically. During summer, the sun rises in the northeast, climbs high overhead at midday, and sets in the northwest, creating a long arc through the sky. During winter, it rises in the southeast, barely climbs above the horizon, and sets in the southwest, tracing a low, short arc. Only during the equinoxes does the sun rise due east and set due west. This changing path means the amount of atmosphere sunlight must pass through also changes. In winter, sunlight travels through more atmosphere, scattering more light and reducing the heating effect, another factor making winters colder. The temperate zones, regions between the tropics and polar circles, experience what many consider just right conditions for human civilization. Here, between roughly 30 and 60 degrees north and south latitude, seasons are pronounced, but not harsh. Winters bring cold but not endless darkness. Summers bring warmth but not scorching heat. These moderate seasonal changes encourage diverse ecosystems and create conditions favorable for agriculture. Most of the world's major civilizations developed in temperate zones precisely because the seasonal rhythm provided reliable growing seasons, natural water storage in the form of winter snow and spring melt, and climates that required humans to innovate, building shelter, storing food, and planning ahead without overwhelming them. Near the equator, a band of intense rainfall and thunderstorms circles the Earth, driven by the sun's direct heat. This band, called the Intertropical Convergence Zone, or ITCZ, doesn't stay fixed in one place. It follows the sun, shifting north during Northern Hemisphere summer and south during Southern Hemisphere summer. This movement creates wet and dry seasons in tropical regions. When the ITCZ moves overhead, heavy rains arrive. When it moves away, dry conditions prevail. This is why many tropical countries don't speak of summer and winter, but rather of rainy season and dry season. The ITCZ demonstrates how the sun's apparent movement, caused by Earth's axial orientation, drives not just temperature changes, but precipitation patterns too. The arrangement of continents on Earth significantly influences seasonal patterns. Large continents in the Northern Hemisphere, North America, Europe, and Asia, create stronger seasonal temperature swings than occur in the Southern Hemisphere, which is mostly ocean. This is because land heats and cools more rapidly than water. The massive Eurasian continent creates some of Earth's most pronounced seasonal contrasts, with regions in Siberia experiencing temperature ranges exceeding 150 degrees Fahrenheit between summer and winter. The Southern Hemisphere, dominated by the Pacific, Atlantic, and Indian Oceans, experiences more moderate seasons. If Earth's continents were arranged differently, our seasonal patterns would change dramatically, even with the same axial orientation. High in the atmosphere, powerful rivers of air called jet streams flow from west to east, helping to drive weather patterns across the mid-latitudes. These high-altitude winds aren't constant in their paths. They shift north and south following the seasonal position of the sunday. During Northern Hemisphere summer, the jet streams shift northward. During winter, they move southward, bringing cold Arctic air down into the mid-latitudes. The position and strength of jet streams determine whether a region experiences a mild or harsh winter, a cool or scorching summer. Understanding how seasonal shifts in solar heating move these atmospheric rivers helps meteorologists predict seasonal weather patterns months in advance. The world's oceans act like a massive heat distribution system, moving warm water from the tropics toward the poles and cold water from the poles toward the equator. These ocean currents are partially driven by seasonal changes in wind patterns, which themselves are driven by the orientation-induced seasonal changes in solar heating. The Gulf Stream, for example, carries warm tropical water northward along North America's east coast and across to Europe, moderating winter temperatures there. Without this current, Europe would be far colder. Seasonal variations in ocean circulation affect weather patterns, fish populations, and even the formation of hurricanes, demonstrating how seasons shape not just the atmosphere, but the entire fluid envelope surrounding Earth. Every winter, vast regions of Earth's surface transform as snow blankets the land and ice forms on lakes and seas. This seasonal ice cover is itself a product of the angle-driven seasons, but it also influences those seasons through feedback effects. fresh snow reflects up to 90% of incoming sunlight back into space, keeping temperatures cold even as spring approaches. This is why snow can persist for weeks after the winter solstice, even though days are growing longer and the sun is climbing higher. As spring advances and snow melts, darker ground is exposed, absorbing more sunlight and accelerating the warming. This cycle of freezing and thawing has shaped landscapes through erosion and deposition for millions of years. For plants, what matters most about seasons is the growing season, the continuous period when temperatures stay warm enough for plant growth, typically defined as days when the average temperature stays above 40 degrees Fahrenheit. At the equator, the growing season lasts all year. At mid-latitudes, it might run from April through October, about 180 to 200 days. In subarctic regions, the growing season might be only 60 days long, a brief window between the last spring frost and first fall frost. This growing season, directly determined by seasonal solar heating patterns, limits what crops can be grown where, shaped the development of agriculture, and continues to define the boundaries of ecosystems and human settlements today. Perhaps the most profound effect of seasons is synchronization, the way seasonal changes coordinate the activities of countless species across entire ecosystems. Trees know when to leaf out, flowers know when to bloom, insects know when to emerge, birds know when to migrate, and mammals know when to reproduce, all timed to the seasonal cycle. This synchronization happens because Earth's orientation creates reliable, predictable patterns that life can adapt to. Spring always follows winter, summer always brings longer days, fall always precedes cold. This reliability has allowed life to develop intricate timing mechanisms that match reproductive cycles, growth phases, and periods of rest to the eternal wheel of seasons turning overhead. If you're still awake, still listening to Earth's secrets, that means curiosity hasn't fully rested yet. And that's okay. Take a gentle breath. Feel the weight of your body on the bed, grounded like ancient stone. We're wandering through nature's quiet wisdom together. And we'll keep going, slowly. Stand on the equator and experience a world where traditional seasons barely exist. Here, day and night are almost always equal length, about 12 hours each, year-round. Temperatures stay warm and consistent because the sun always passes nearly overhead at midday. Instead of summer, fall, winter, and spring, equatorial regions experience wet and dry seasons as the intertropical convergence zone shifts north and south. These wet-dry cycles can be just as dramatic as temperature-based seasons elsewhere, with months of torrential daily rainfall alternating with months of relative drought. Equatorial ecosystems, including rainforests, evolved in this world of constant warmth and seasonal moisture changes rather than temperature swings. Inside the Arctic Circle during summer, the sun never sets. It just circles the sky, dipping close to the horizon at midnight but never disappearing. Living under the midnight sun feels dreamlike and otherworldly. Your body's natural sleep-wake cycle, calibrated to expect darkness at night, becomes confused. Many Arctic residents experience sleep disruption and find they need blackout curtains to simulate nighttime. Yet there's also a strange magic to it. Working or playing in sunlight at 3 in the morning, watching the sun hover above mountains at midnight, seeing shadows rotate around you throughout the day. This phenomenon exists only because Earth leans so dramatically that polar regions can face the sun continuously as the planet rotates. The opposite condition, polar night when the sun doesn't rise for months, creates different challenges. In Barrow, Alaska, now called Utqiagvik, the sun sets in mid-November and doesn't rise again until late January. For 65 days, residents live in twilight and darkness. Vitamin D deficiency becomes a concern without sunlight. Seasonal affective disorder affects many people. Yet human communities have thrived in these conditions for thousands of years, developing cultural adaptations, artificial lighting, and social structures to cope with extended darkness. Animals face similar challenges, with some hibernating through polar night, others migrating away, and some adapted to hunt and survive in perpetual darkness using other senses. Climb a mountain and you'll pass through multiple seasons in a single day. At the base in summer, conditions might be warm and green. Halfway up, you enter cooler temperatures equivalent to spring or fall. Near the summit, you might find winter conditions with snow and ice, even in July. This altitudinal zonation creates what ecologists call sky islands, habitats isolated by elevation that mimic conditions found hundreds of miles north or south. Mountains in tropical regions can have permanent glaciers on their peaks, even though the land below never experiences winter. This vertical compression of seasons allows unique ecological communities to exist in close proximity. Deserts experience seasons differently than temperate regions. Many deserts are hot year-round, with seasonal changes more about rainfall than temperature. The Sonoran Desert of Arizona and Mexico has a monsoon season in summer, when brief but intense thunderstorms bring most of the year's precipitation. Winter brings a second rainy period with gentler, soaking storms. Desert plants and animals key their life cycles to these moisture patterns rather than temperature changes. Seeds that have waited years suddenly germinate after a good rain, creating spectacular spring wildflower displays. This is still a seasonal pattern, just driven more by Earth's shifting weather belts than by direct changes in solar heating. Two invisible lines circle Earth at 23.4 degrees north and south latitude, the tropics of Cancer and Capricorn. These marks represent the farthest north and south that the sun can appear directly overhead. On the summer solstice, the sun shines straight down at the Tropic of Cancer. On the winter solstice, it does the same at the Tropic of Capricorn. Between these lines lies the tropical zone where the sun appears overhead twice per year. Beyond these lines lies the temperate zones where the sun is always at a slant. As Earth's inclination slowly changes over 41,000 years, these tropics shift slightly north and south. Currently, they're moving about 50 feet closer to the equator each year. Tropical rainforests near the equator might seem seasonless, but they have subtle rhythms. Many rainforest trees produce fruit on precise annual schedules, providing food pulses that animals depend on. Some trees flower only once a year, synchronized with seasonal changes in day length that are almost imperceptible, a shift of just minutes throughout the year. Rainfall patterns create distinct wet and dry periods that govern when rivers flood, when certain insects emerge, and when birds nest. These seasonal signals are muted compared to temperate regions, but they're real and crucial. Rainforest organisms are exquisitely tuned to detect tiny seasonal cues that travelers might not even notice. Both polar regions experience dramatic seasonal light and darkness, but their seasons differ in important ways. The Arctic is an ocean surrounded by land, while Antarctica is a continent surrounded by ocean. This means the Arctic stays slightly warmer because the ocean holds heat, while Antarctica becomes intensely cold. The coldest temperatures on Earth, below -100 degrees Fahrenheit in winter. The Arctic supports diverse wildlife including polar bears, seals, and whales. Antarctica's interior is largely lifeless, except at the coasts. These differences show that while Earth's orientation drives seasons everywhere, local geography and geology dramatically modify how those seasons manifest in different locations. Sometimes in late winter, a warm spell arrives, melting snow and fooling plants into breaking dormancy early. Then freezing temperatures return, potentially killing exposed buds and early growth. This phenomenon, called false spring, can devastate fruit crops and natural ecosystems. It's becoming more common as Earth's climate changes, with winter temperatures becoming more variable. Plants evolved over millions of years to respond to reliable seasonal cues, particularly the length of daylight. But temperature volatility confuses these ancient timing mechanisms. A peach tree might sense warm February days and begin preparing to bloom, then suffer damage when March brings hard frosts. Understanding seasons helps us predict and prepare for these ecological disruptions. We're halfway through our journey, and here's an important truth emerging. While Earth's orientation remains constant year to year, the character of seasons is changing. Studies of climate patterns and phenology through 2024 and 2025 show spring arriving earlier, by approximately 1 to 2 weeks compared to mid-20th century baselines in many temperate regions. Fall extends later. Growing seasons lengthen. These changes happen not because Earth's angle is different, but because average temperatures have increased due to greenhouse gases trapping more of the sun's heat. The ancient rhythm of seasons continues, but the temperature and precipitation patterns overlaid on that rhythm are shifting, creating mismatches between plant bloom times, pollinator emergence, and bird migration schedules that have evolved over millions of years. And imagine, even when everything seems empty, space is always full of waves, vibrations, invisible energy. The space inside and around you is never truly empty. Imagine you're floating on a calm lake, but beneath the surface, there's always gentle current. Now we continue the journey. Plants can tell time. Inside every plant cell are molecular clocks that track the 24-hour day-night cycle. But plants also have longer-term timing mechanisms that measure the annual cycle of seasons. They sense the changing length of daylight using special proteins called phytochromes that detect red and far-red light. As autumn days shorten, phytochromes trigger the production of abscisic acid, a hormone that tells the plant to prepare for winter, stop growing, seal off leaves, harden tissues against cold. This molecular clock is so precise that plants know what month it is within days. These timing systems evolved over millions of years to synchronize with Earth's reliably tilted journey around the Sunday. Every autumn in temperate regions, a transformation sweeps across the landscape as deciduous trees shed their leaves. This isn't death, it's a survival strategy. Keeping leaves through winter would be deadly for these trees. Frozen water in leaf cells would rupture cell walls, killing the tissue. Leaves continue losing water through evaporation even in winter, and frozen ground prevents roots from replacing it, causing lethal dehydration. So as daylight shortens, trees withdraw valuable nutrients from leaves back into branches and trunk, seal off each leaf's connection point with a corky layer, and let them fall. Bare branches survive winter in dormancy, metabolizing slowly, waiting for spring to rebuild. Those brilliant autumn colors, reds, oranges, yellows, result from trees dismantling the green chlorophyll in their leaves before dropping them. Chlorophyll normally masks other pigments present in leaves. As chlorophyll breaks down, yellow and orange carotenoids that were always there become visible. Red anthocyanins are newly produced in autumn, possibly to protect leaves during the withdrawal of nutrients. The intensity of autumn color depends on weather conditions. Cool nights and sunny days produce the brightest displays. Recent research shows that warmer autumn temperatures may reduce color intensity by disrupting the biochemical processes of leaf senescence, potentially creating duller fall displays as climate patterns shift. True hibernation is more than sleep. It's a profound metabolic shutdown that allows certain mammals to survive months without food. A hibernating groundhog's heart rate drops from 80 beats per minute to just 5. Its body temperature falls from 98 to 38 degrees Fahrenheit, barely above freezing. Breathing slows to one breath every several minutes. Metabolism drops to 2% of normal rate. The animal survives by slowly burning fat stored during summer and fall. Hibernation is triggered by shortening days and cooling temperatures. seasonal cues telling animals that winter is approaching. Recent studies show that climate warming is shortening hibernation periods and changing when animals enter and emerge from their winter dens. Billions of birds migrate between summer breeding grounds and winter feeding areas, navigating thousands of miles with remarkable precision. They time these journeys using multiple cues, changing day length, temperature shifts, food availability, and even Earth's magnetic field. Many species have innate calendars that tell them when to start migrating, even when kept in laboratory conditions without environmental cues. Arctic terns travel from Arctic to Antarctic and back each year, about 44,000 miles, following an eternal summer as they commute between opposite poles. Migration allows birds to exploit seasonal abundances of food and suitable habitat, following spring northward and fleeing winter southward, their lives choreographed by Earth's tilted spin. Monarch butterflies have one of nature's most elegant responses to seasons. Those emerging in late summer differ from their spring and early summer relatives. They live 8 months instead of 8 weeks, don't reproduce immediately, and possess an urge to fly south. These supergeneration monarchs migrate up to 3,000 miles from Canada to Mexico, spending winter in dormancy in mountain forests before flying north in spring to breed. Their descendants, 2 or 3 shorter-lived generations, make the return journey northward throughout spring and summer. This means no individual monarch completes a full migration cycle. Rather, the species as a whole follows a multi-generational seasonal choreography, responding to cues from diminishing daylight. Many insects survive winter through diapause, a dormant state similar to hibernation. Diapause can occur at any life stage: egg, larva, pupa, or adult, depending on the species. During diapause, development stops, metabolism slows, and the insect becomes highly resistant to cold and dehydration. Some insects produce glycerol, a natural antifreeze that prevents ice crystal formation in their cells. Others can survive being frozen solid, with special proteins preventing ice from damaging cellular structures. Diapause is typically triggered by shortening day length in autumn, a reliable signal that winter approaches. This allows insects to time their dormancy correctly, entering it before killing frosts arrive and breaking it as spring warming begins. Even cold-blooded fish respond to seasons. Salmon spend years in the ocean but return to freshwater streams to spawn at specific times of year. Their migration triggered by day length and temperature. Bass and pike adjust their activity levels seasonally, becoming lethargic in cold water and active in warm water because their metabolism depends on environmental temperature. Some fish change depth seasonally, moving to deeper, cooler waters in summer and shallower waters in other seasons. In frozen lakes, fish congregate in the deepest spots where water remains liquid at 39 degrees Fahrenheit, the temperature at which water is densest, and sinks to the bottom, creating a warmer layer beneath the ice. Wood frogs have evolved an astonishing adaptation to winter. They allow themselves to partially freeze. As temperatures drop, ice forms in the frog's body cavity and between muscles, but special proteins and high concentrations of glucose protect cells from freezing solid. The frog's heart stops, breathing ceases, and brain activity halts. Up to 65% of the frog's body water can freeze, yet it survives. When spring warmth arrives, the frog thaws from inside out, its heart restarting, and metabolism resuming as if waking from sleep. This freeze tolerance allows wood frogs to survive winters even in Alaska, demonstrating the remarkable adaptations that seasonal conditions can drive in evolution. Many mammals in seasonal climates grow winter coats, thicker, denser fur that provides better insulation against cold. Some, like snowshoe hares and Arctic foxes, also change color, turning white in winter for camouflage against snow. and brown in summer to match earth and vegetation. These changes are triggered by day length rather than temperature, ensuring the animals prepare for winter before it arrives, rather than reacting after cold sets in. As days shorten in autumn, hormonal changes stimulate hair follicles to grow denser winter fur and produce different pigments. The process reverses in spring. This reliance on photoperiod means climate warming doesn't disrupt the timing of coat changes, though it may create mismatches. Despite popular belief, bears don't truly hibernate. They enter a state called torpor, a lighter dormancy where body temperature drops only 10 to 15 degrees, instead of the 30 to 40 degree drop seen in true hibernators. A bear's heart rate slows from 40 to 8 beats per minute, and it doesn't eat, drink, urinate, or defecate for months, surviving on stored fat. But bears can wake quickly if disturbed, whereas true hibernators need hours to raise their body temperature enough to become active. Female bears even give birth during winter torpor, nursing cubs while remaining dormant. This impressive adaptation allows bears to survive long winters when their primary foods, berries, nuts, fish, become unavailable. Pine, spruce, and fir trees keep their needles year-round, even through harsh winters. How do they survive when deciduous trees cannot? Their needles have thick, waxy coatings that reduce water loss and resist freezing. Narrow needle shape minimizes surface area exposed to cold, drying winds. The needles contain antifreeze chemicals that lower their freezing point. Evergreens can photosynthesize during warm winter days when deciduous trees cannot, giving them a competitive advantage in short growing seasons. This strategy works well in northern latitudes and high elevations where growing seasons are brief. Keeping needles requires less energy than growing new leaves each spring, allowing evergreens to thrive where rapid growth is impossible. Tulips, daffodils, and crocuses survive winter underground as bulbs, compressed storage organs packed with energy. In autumn, these plants die back completely above ground, withdrawing all resources into the bulb below the frost line. The bulb remains dormant through winter, protected by soil insulation. Many bulbs require a period of cold, a chilling requirement, before they can bloom, ensuring they don't sprout during warm autumn weather, only to be killed by later frosts. When spring warmth penetrates the soil, bulbs rapidly send up leaves and flowers using stored energy, blooming before trees leaf out and shade the forest floor. This strategy allows spring ephemerals to dominate briefly, completing their life cycle before summer arrives. In temperate oceans, spring brings an explosion of microscopic plant life called phytoplankton. These tiny organisms bloom when three conditions align: increasing sunlight, warming water, and nutrients. Brought up from depths by winter storms, spring phytoplankton blooms are so massive they're visible from space as turquoise swirls covering thousands of square miles. These blooms form the foundation of ocean food webs, feeding zooplankton, which feed small fish, which feed larger fish and whales. The seasonal pulse of phytoplankton growth, driven by seasonal changes in light and ocean mixing, determines when and where fish spawn, whales migrate, and seabirds nest, demonstrating how seasons coordinate marine life. Many animals time reproduction to seasons, giving birth or hatching young when food is most abundant, and conditions optimal for survival. Deer fawns are born in late spring, when new plant growth provides nursing mothers with nutritious food. Songbirds nest when caterpillars emerge to feed on fresh leaves, providing protein-rich food for nestlings. Salmon spawn in autumn, and their eggs incubate through winter, hatching in spring when streams come alive with insect life. This seasonal timing is crucial. Offspring born at the wrong time may starve or freeze. Animals use day length, temperature, and food availability as cues to trigger reproductive hormones, ensuring the next generation arrives when conditions favor survival. The Arctic ground squirrel survives the far north's brutal winters through the most pronounced hibernation known. Its body temperature drops below freezing, sometimes to 27 degrees Fahrenheit, without freezing solid, a process called supercooling. The animal exists in this suspended state for up to 8 months, taking only 1 or 2 breaths per minute. During this time, it doesn't eat or drink at all. Periodically, every few weeks, the squirrel's body automatically warms up for 12 to 24 hours before cooling again. These arousals may allow the animal to sleep normally, since the hibernating brain can't complete normal sleep cycles. This remarkable adaptation allows life to persist even in harsh seasonal cold. Trees in seasonal climates grow in pulses, creating annual rings visible in their trunks. Each year adds 1 ring. Wide, light-colored spring wood grown rapidly when water is abundant, and narrow, dark-colored summer wood grown slowly as conditions become drier. Counting rings tells a tree's age. Studying ring width reveals climate history. Wide rings indicate good growing years with ample water. Narrow rings signal drought or harsh conditions. Old trees are climate libraries, with their ring patterns recording centuries of seasonal variation. Scientists use tree rings to reconstruct past climates, understanding how seasons varied long before humans kept weather records, revealing patterns of drought, floods, and temperature changes throughout history. Even in deserts where seasons are subtle, cacti respond to seasonal moisture patterns. Many cacti grow actively during summer monsoon season, when brief rains arrive, storing water in their accordion-pleated stems that expand as they fill. During the long dry season, cacti enter dormancy, barely growing, their metabolic rate slowing to conserve resources. Some cacti flower in response to seasonal cues, after sufficient winter chilling or when summer rains arrive. The saguaro cactus produces flowers in late spring, timed to when bats and birds migrate through, ensuring pollination. This demonstrates that even in environments where temperature varies little, organisms evolve to track seasonal patterns in moisture and respond accordingly. Migration routes followed by animals today were established thousands of years ago, perhaps even longer. Caribou in North America travel the same corridors their ancestors used, following paths between winter and summer ranges that may have originated during ice ages. Wildebeest in Africa circle the Serengeti in an endless loop, following seasonal rains and fresh grass. These routes persist because they connect seasonal resources, places where food, water, and safety align with the turning of seasons. Young animals learn migration paths from their elders, creating knowledge chains stretching back generations. These routes are biological highways, maintained not by pavement, but by memory, instinct, and the reliable rhythm of seasons. Temperate lakes undergo a remarkable seasonal transformation called turnover. In summer, lakes stratify into layers. Warm surface water floats above cold deep water, with little mixing. This isolates the deep water, which gradually becomes oxygen depleted. When autumn cooling chills the surface, the temperature difference disappears and wind can mix the entire lake, bringing oxygen down and nutrients up, the fall turnover. A similar process happens in spring. These seasonal turnovers are crucial for lake ecology, redistributing oxygen and nutrients, allowing fish to access deep water and resetting the system. Climate warming is disrupting turnover patterns, with some lakes remaining stratified longer, threatening the seasonal renewal cycles that aquatic life depends on. Beneath our feet, soil biology follows seasonal rhythms. In spring, warming soil awakens billions of bacteria, fungi, and invertebrates that decompose dead leaves and wood, releasing nutrients for plant growth. Summer heat accelerates decomposition but can slow it if conditions become too dry. Autumn leaf fall provides a feast of organic matter, Winter cold slows soil organisms to near dormancy, preserving organic matter for spring. This seasonal cycle of decomposition and nutrient release synchronizes with plant growth cycles. Nutrients become available just when plants need them. Earthworms move up and down in the soil profile seasonally, staying active near the surface when conditions are favorable and retreating deeper during drought or frost. Humans, too, respond biologically to seasons. Some people experience seasonal affective disorder, SAD, a form of depression that arrives with autumn's shortening days and lifts with spring's return. SAD affects about 5% of Americans, with symptoms including low energy, oversleeping, weight gain, and depressed mood. It appears to result from disrupted circadian rhythms and altered serotonin and melatonin levels caused by reduced sunlight exposure. This condition demonstrates that humans haven't escaped seasonal influences despite our indoor lifestyles and artificial lighting. Our brains still register seasonal changes in day length, affecting mood and behavior, a reminder that we remain biological creatures connected to Earth's ancient rhythms. Your immune system changes with the seasons. Scientific studies of human immune function reveal seasonal activity patterns, with inflammatory genes more active in winter months and anti-inflammatory genes more active in summer, which may partially explain seasonal patterns in illness. This may help explain why colds and flu peak in winter, not just because we're indoors more, but because our immune systems respond differently to seasonal cues. Vitamin D production, dependent on summer sunlight, affects immune function. Some autoimmune conditions worsen in winter. Even our gut bacteria populations shift seasonally. These patterns suggest that despite modern life's consistency, our bodies still track seasons at a molecular level, preparing for seasonal challenges our ancestors faced for millions of years. Human civilization arose when we learned to harness seasonal patterns through agriculture, planting in spring when soil warms, tending crops through summer, harvesting in fall before frost, storing food through winter. This seasonal cycle enabled permanent settlements and complex societies. Different crops require different day lengths to flower, allowing farmers to choose varieties suited to their latitude. Winter wheat is planted in fall, requires winter cold to trigger flowering, then matures in spring. Rice requires long summer days and warm temperatures. Understanding seasonal patterns determines what grows where, shaping human cultures and cuisines. Agricultural calendars, based on seasonal markers, solstices, equinoxes, first frost dates, organized human life for thousands of years. As we approach Fact 75, something becomes clear. Seasons are not just astronomical phenomena or weather patterns. They are a planetary symphony, where Earth's orientation conducts countless life forms in coordinated response. Trees bud, insects emerge, birds migrate, frogs sing, flowers bloom, seeds scatter, leaves fall, all timed to seasonal changes with remarkable precision. This synchronization emerged through millions of years of evolution, with natural selection favoring organisms that correctly read seasonal signals and responded appropriately. The result is a living world choreographed by Earth's tilted journey around the sun, a dance so complex yet so reliable that it forms the fundamental rhythm of the biosphere itself. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spring follows winter. Summer follows spring. Fall follows summer. Winter returns. Around and around, endless cycles. Like your breath, inhale, exhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like seasons silently rotating in their orbits, unhurried, unresisting, simply existing, We're almost there now. Seasons teach patience. Spring doesn't rush. It arrives according to laws written in planetary motion billions of years old. You cannot force buds to open early. Seasons teach acceptance of time's passage and change's inevitability. They show that endings, autumn, winter, are necessary preludes to beginnings. Ancient philosophies recognized these lessons, using seasonal metaphors: youth as spring, maturity as summer, aging as autumn, rest as winter, with renewal implied in the cycle's return. Every culture with distinct seasons has created poetry around them. Japanese haiku traditionally includes seasonal references. Western poetry overflows with seasonal imagery: spring as renewal, autumn as change. These metaphors work because seasons are universal human experience, shared across time. When you read a 1,000-year-old poem about spring's first leaves, you feel what the poet felt, because spring today follows the same patterns it did then. Seasons connect us across time. Humans worldwide celebrate seasonal turning points, solstices and equinoxes marking the year's corners, winter solstice festivals celebrating the return of light, Christmas, Hanukkah, Yule. Spring equinox festivals honor renewal, Easter, Nowruz, Holi. Harvest festivals thank for autumn's abundance, Thanksgiving, Sukkot. These celebrations arose independently because humans everywhere share the same tilted planet and recognize the significance of seasonal changes. Seasonal festivals remind us we are part of something larger and older. Light quality changes with seasons, not just quantity but quality. Summer light feels bright, with the sun high overhead. Winter light feels soft and gentle, the low sun creating long shadows and golden tones. Photographers treasure golden hour, but this light persists longer in winter when the sun stays low. Artists throughout history have captured seasonal light: Impressionists painting summer's brilliance, Dutch masters capturing winter's softness. This changing light affects mood, making summer feel energized and winter introspective. Notice how time feels different in different seasons. Summer seems endless to children on vacation, days stretching lazily. Winter feels compressed, dark, and hurried. This relates to daylight hours and activity levels. Long summer days pack more experiences and feel longer in memory. Short winter days blur in darkness. Seasons mark time's passage. Completing 4 seasons means 1 year, an orbit completed. This is how humans tracked time before clocks: planting time, growth time, harvest time, rest time, then beginning again. There is deep comfort in seasons' predictability. After winter's darkness, spring will come, not might come, will come, with the certainty of physics. This predictability provides psychological stability. No matter how harsh this winter, spring waits on the other side. Seasons remind us that difficult times pass, pleasant times return. Change is constant, but not chaotic. Perhaps this is why seasonal disruption feels so unsettling. It threatens a pattern we've relied on since our species' beginning. Food tastes better in season: ripe tomatoes in summer, pumpkins in fall, citrus in winter. This isn't nostalgia, it's biology. Fruits evolve to ripen when conditions favor their dispersal. Summer tomatoes taste sweet because they ripened naturally in abundant sunlight. Winter strawberries lack flavor because they didn't experience the right light and temperature cycles. Eating seasonally means eating foods fresh and nutrient-rich, connecting us to place and time, to local ecosystems and their seasonal rhythms. Your memories are tagged by season. That summer you moved, the winter you got sick, the spring you fell in love. Seasons provide context and structure to memory, organizing personal history into cycles rather than lines. This makes evolutionary sense. Remembering what happened last spring helps prepare for next spring. Your life story unfolds, not as a straight line, but as a spiral. circling through seasons, each path different yet familiar, connecting memories across time. Many people notice their creativity shifting with seasons. Some feel most creative in winter's dark, introspective months, turning inward to produce art. Others bloom with spring, inspired by renewal. Summer's long days and social energy spark different creativity than autumn's reflective mood. These patterns vary individually, but suggest that seasonal changes in light, temperature, and social rhythms affect creative cognition. Seasons shape not just when we plant and harvest, but how we think and create meaning. Children experience seasons intensely, because each season represents a larger fraction of their lived experience. A 6-year-old has only known 6 winters, making each one significant. Children delight in seasonal markers: first snow, first flowers, school ending, that adults overlook. They see seasons not as obstacles but as adventures, each bringing unique possibilities. This childlike attention might be worth reclaiming. It connects us to the present moment and to Earth's rhythms, reminding us that seasons are the very structure of time. People who move from seasonal climates to tropical ones often report missing seasons, feeling unmoored without their rhythmic markers. Endless summer seems appealing, but can feel static, unchanging. The human brain craves seasonal variation, the rhythm of change. Similarly, people moving from tropics to strongly seasonal climates must adjust to dramatic annual swings. These feelings suggest seasons are part of how we structure experience. They provide natural checkpoints, opportunities for reflection and renewal, cycles of activity and rest. Pull back and see it clearly. You're on an angled planet spinning through space at 67,000 miles per hour as it circles a burning star. The orientation, an accident from a collision billions of years ago, means one side, then the other, leans into the star's radiation. This creates moving patterns of heat and cold, light and dark, abundance and scarcity that sweep across the surface. Life responded by evolving sensitivity to these patterns, creating a living world that breathes and sleeps in rhythm with planetary geometry. Seasons operate beyond human scale, following rhythms established billions of years ago. Whether we notice them or ignore them, celebrate them or curse them, seasons continue their patient turning. This indifference to human concern, paradoxically, provides comfort. We participate in patterns far larger than ourselves, temporary guests in an ancient dance. Knowing seasons existed long before consciousness, and will continue long after, reminds us we're part of something vast, enduring, and beautiful, unfolding according to laws written in gravity and light. Every organism on Earth experiences the same seasons, governed by the same orientation. A maple tree in Maine and a person in Tokyo both sense spring arrive as Earth's northern hemisphere leans sunward. A penguin in Antarctica and a polar bear in the Arctic both endure winter darkness when their hemispheres lean away. This shared experience, synchronized across species, latitudes, and hemispheres, creates planetary unity. We are all riding the same angled world through space, all responding to the same ancient rhythm. We asked at the beginning, why do seasons change? Now the answer is clear, because Earth leans at 23.4 degrees, spinning through its orbit, bringing first one hemisphere, then the other, into the sun's direct embrace. But more deeply, seasons change us. They teach patience, mark time, inspire creation, structure memory, drive evolution, and connect us to something larger. Understanding seasons means understanding that you live on a dynamic planet, that change is built into existence, that endings enable beginnings. Perhaps humans carry an internal seasonal rhythm, not just responding to external seasons but somehow embodying them. We speak of people having sunny dispositions or going through dark winters of the soul, We describe career stages as spring for beginnings and autumn for maturity. These metaphors feel true because seasons are such fundamental patterns that they've become woven into how we understand existence itself. The angled planet that creates external seasons also created minds that think in seasonal metaphors. Earth's orientation is slowly changing, moving toward a minimum about 10,000 years from now. Future seasons will be milder, with less pronounced temperature differences. This will happen so gradually that no single generation will notice, but over millennia, it will reshape ecosystems. Meanwhile, human-caused climate change is altering seasons now. Springs arriving earlier, autumns extending later. The ancient rhythm continues, but the melody is changing. Our children will experience different seasons than we did. A reminder that while patterns persist, nothing remains exactly the same. Part of season's wisdom is accepting loss. Every autumn, trees release what they've grown all summer. Tons of leaves, months of work. They don't cling. They let go, trusting spring will come again. Animals burn fat reserves. Birds abandon territories. Flowers drop seeds and die. This willing acceptance of loss, this trust in cycles' continuation, offers a lesson. Perhaps we too can practice releasing what must be released, trusting that endings create space for arrivals, that winter is rest's embrace before renewal. Winter, often seen as harsh, is actually a gift. It forces rest when organisms need recovery. It kills pathogens that might otherwise overwhelm ecosystems. It synchronizes reproduction so offspring arrive together in spring. It provides contrast that makes spring's warmth feel miraculous. Without winter, there would be no spring renewal, no summer abundance, no autumn harvest, just endless sameness. Winter is part of life's rhythm, the rest between heartbeats, the pause between breaths, the darkness that makes light visible. Becoming aware of seasons, really aware, not just noting weather but sensing Earth's position, feeling sunlight's angle, noticing when birds return, is a form of meditation. It connects you to place and time, to the planet's motion through space, to cycles larger than daily concerns. This awareness was once necessary for survival. Now it's a choice that enriches life. Notice when the sun rises, where it sets, how shadows fall. Watch for seasonal markers. This attention grounds you in the physical world. Many spiritual traditions consider seasons sacred, viewing them not as mechanical outcomes, but as expressions of deeper order. The reverence isn't unscientific. It's recognizing that seasons represent something profound, the reliable unfolding of pattern, the interplay of constancy and change. A solstice is simultaneously a precisely calculable astronomical event and a moment of significance. The mechanics don't diminish the meaning, they deepen it. That such beauty arises from simple physics. An angle, an orbit, a star, suggests elegance is woven into existence's basic structure. You are fundamentally a seasonal creature, even in climate-controlled comfort, eating strawberries in January. Your genes carry adaptations forged over millions of years, responding to seasons. Your ancestors survived ice ages and warm periods, adapting to seasonal conditions. That history lives in you, in vitamin D metabolism responding to summer sun, in immune patterns shifting with season, in circadian rhythms tracking day length. You can ignore seasons, but you can't escape them. They're written into your biology, part of your inheritance. If you could hear Earth's journey through space, it might sound like music, a four-movement symphony playing once per year. Spring's movement, awakening, tentative, building. Summer's movement, bold, expansive, full of energy. Autumn's movement, reflective, bittersweet, slowing. Winter's movement, quiet, minimal, preparing for spring's return. This isn't fanciful. It's accurate. Seasons have rhythm, tempo, dynamics. They repeat with variation, like a song played with different interpretation. You've heard this song your entire life, structuring time itself. Nothing stays. Summer's heat fades, winter's cold passes, spring's flowers wilt, autumn's leaves fall. This impermanence can distress or comfort depending on perspective. Seasons teach that change is not aberration, but nature's fundamental mode. Yet within change, patterns persist. Summer always follows. Spring, the cycle continues. So seasons teach both impermanence and continuity, showing that what changes does so within structures that endure. This paradox, constant change within reliable pattern, describes not just seasons, but existence itself, helping us accept change while trusting underlying order. Why do seasons change? Because Earth leans at 23.4 degrees as it orbits the Sunday. But more deeply, seasons change because that's how this universe arranges matter and energy into pattern. The orientation that creates seasons also created conditions for life to flourish, for consciousness to emerge. You're here, aware of this seasonal moment, because billions of years ago a collision nudged a planet sideways. That accident became Earth's rhythm. Seasons are change itself, endlessly cycling, teaching that what leaves will come again. Rest now. And so, our quiet journey through Earth's seasons comes to a gentle close. We've traveled from that ancient collision that tilted our world sideways, to the trees measuring daylight with molecular precision, discovering along the way that seasons are both physics and poetry. From the Arctic's midnight sun to a butterfly's multi-generational migration, we've glimpsed how seasons are both measurable and mysterious, predictable yet profound. Seasons remind us that change is the only constant. Much of nature's deepest wisdom happens in silence, underground in dormant roots, inside folded buds, beneath winter snow, in the patient orientation of a planet through space. They teach us patience, acceptance, and trust in cycles. By pausing to notice, we glimpse the extraordinary in the ordinary. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about how water cycles through clouds, rivers, oceans, and rain. Everything is connected, everything returns, everything flows. You are part of that flow, that cycle, that eternal return. Let your entire being dissolve into the rhythm of nature, into the breath of the earth, into stillness. Prepare for deep sleep. No boundaries left, only peace. If these calm stories from Earth helped you breathe a little easier, passing them along could help another tired soul drift into rest. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of seasons to fade now, like autumn leaves spiraling down through still air, leaving only gentle calm behind. Let your breathing deepen. Let your body feel heavier, as if Earth's gravity has grown stronger, pulling you softly into rest. If sleep comes, let it carry you like a leaf on water, smoothly, inevitably, into a realm where time and seasons no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, the seasons will still be there. Earth will still lean. The sun will still rise. Spring will still follow winter. But tonight belongs to stillness. Rest well, fellow traveler. And remember, you are part of the eternal dance, a brief awareness carried on a tilted world through infinite space, connected to everything that blooms and sleeps and blooms again. Fall asleep to gentle facts, where science meets sleep. Good night.